In this lecture, we will discuss different stiffening concepts for thin-walled shells and provide you with some guidelines to help you select the appropriate stiffener concept for your design. A shell structure is defined as a flat or slightly curved sheet with stiffeners, such as the one I have here. As you can see, there are many different types and shapes of stiffeners, which allows us to optimize our design. Here we see an L-shaped, a Z-shaped and two head-shaped stiffeners. Each stiffener geometry gives rise to different behavior of the shell structure under compression. The head stiffeners in the picture have a higher stability, meaning they have more resistance to buckling than the L-shaped stiffeners. They will bulge out on the non-clamped side, as you can see. Next to the shape of the stiffener, we can also vary their number, and therefore how far they are spaced apart. If we were to add one stiffener to a panel, the effect of stiffening is limited and only has a local effect on the stability of a shell. Depending on the shape or geometry of a stiffener, it is possible to determine an effective width, which allows you to choose a suitable stiffener spacing. The preferred shape of a stiffener depends on both the type of load and its manufacturing method. It is an optimization between cost, availability, experience of the manufacturer and the loads to be carried. The choice is always a trade-off. Now it's your turn. Please select the stiffener geometry for the upper and lower side of an aircraft wing from the options given here. Which of these stiffeners would you choose and why? You have as options a Z, a J, a Y and an I, a hat, a more curvy Z, a more curvy hat and an inverted head stringer. Pause the video here and think. Difficult choice, eh? Let me take you through the answers, starting with the upper wing panels. In flight, wings bend upwards, causing compression in the upper side of the wing. This is why, in heavy loaded structures, such as the upper wing panels, head stiffeners are often applied. In structures that carry less compressive loads, L-shaped or Z-shaped stiffeners are used, such as in the lower wing panels. Not only does it use up less material, they are also easier to inspect from all sides than head stiffeners that cannot be inspected internally. Now let us take a look at the fuselage. A fuselage has three types of stiffeners to keep its shape and carry the load. Stringers, such as the ones in wings, longerons, heavy longitudinal stiffeners effectively combining several stringers, and frames to maintain the circumferential shape. In the photo here you can see inverted head stringers. Using them this way, they are more inspectable. The curve at the rim of the head is added to give more stiffness. With the presence of both stiffeners and frames, we have to face the issue that they intersect. Also, loads are not constant throughout the fuselage, which means that the thickness of the fuselage panels will vary, as will the stringers. As the outside of the fuselage has to remain even and smooth for aerodynamic reasons, the thickness steps are dealt with on the inside. This is often done by adding extra layers of thickness by making use of doublers, which are riveted or bonded to the structure. The stringers attached to the skin will also have to follow that thickness step. They are then joggled as is shown in the figure here. A fuselage is rarely made out of one piece, but at the same time we want the longitudinal stringers to be as undisturbed as possible. So what tends to happen is that stiffened panels are joined together, and at that same time the stringers are joined together. As you can see here in the figure, the skin is joined on the inside by a splice plate. The stringers are joggled to allow for the splice plate, and the stringers are attached to each other using a stringer splice. Frames and stringers also intersect. Ideally, the stringer is left undisturbed and the frame design is adjusted. This is done by either creating an opening in the frame for the stringer to go through, which implies a weakening of the frame locally, or by floating the frame on top of the stringers, attaching it to the skin using clips. In conclusion, it is safe to say that designing a stiffened panel requires juggling many different requirements to come to a safe, functioning, makeable and affordable compromise.